See, this is hydrogen bonding. So most likely this could be the last topic of this chapter. So hydrogen bonding, see, this is not a real chemical bond. See, this is basically a molecular interaction. So we can say hydrogen bonding is not a real chemical bond. It is a molecular interaction, right? A kind of molecular interaction molecular interaction involving hydrogen. So simply you can say this, that it is a kind of molecular interaction. But in this molecular interaction, there are so many kinds of molecular interaction we have, like dipole-dipole interaction, ion-dipole interaction, and dipole-induced dipole interaction, instantaneous dipole-induced dipole interaction. But which kind of interaction is this? So basically, this involves two kinds of molecular interaction. First is ion dipole. dipole. This point is mandatory. Involving hydrogen means this interaction definitely involves hydrogen. Without hydrogen, if there is any interaction, that is not hydrogen bonding. So ion dipole interaction. This is first kind of hydrogen bond, and second one is dipole-dipole interaction. Dipole-dipole, right? Interaction. So see, one example I am giving you of this. Suppose that if we have F minus, and this is an ion, and HF molecule, right? If we have HF molecule and F minus ion, so what is the polarity of this here? H positive and F minus. So there is a interaction between these two. As you know, there is no interaction between F and F. So only the possible interaction is between F minus and this H. So this interaction is known as a hydrogen bond. See, involving hydrogen. Hydrogen is must. See. So here this is an example of ion dipole interaction. Although the ion dipole interactions are very less, very few examples we have. So this is known as KHF2, basically K plus and HF2 minus. So and you know, in this kind of interaction, the bond energy of hydrogen bond is the highest. Means if ion dipole interaction involving hydrogen is taking place anywhere, then here the hydrogen bond is the strongest hydrogen bond. And dipole-dipole interaction, see another example. This is introduction, so I will come to point slowly. Dipole-dipole interaction, suppose that if we are taking this O H H, so this is a one dipole, delta positive, delta negative, and second molecule of water, this is delta negative. So some kind of interaction is also here between these two hydrogen. So this is called dipole interaction. This is also a hydrogen bond because this involves hydrogen, right? So hydrogen bonds are kind of dipole interaction in majority of cases. In some cases you may get ion dipole interaction. So we can express this hydrogen bonds like this: X, H, and Y, right? And this is delta plus and delta minus. So this kind of interaction, if your system has, so this is known as hydrogen. So in this case, there is a molecular association. So hydrogen bonding, this you can say could be the cause of intermolecular force, one of the very strong cause of intermolecular force. What are X and Y? X and Y may be, both may be same or different, that hardly matter. X and Y both could be fluorine, oxygen, nitrogen, sulfur, chlorine, and sometimes this C triple bond C also sometime will acts as a, as a X or Y could be, right? And benzene ring also could be the place of X or Y. So both may be same, means here O and O you can take, here F and F you can take. See here I have taken here F and F, and here you can take O and O, O and N, whatsoever more electronegative groups. See, as you know, this must have this delta positive, because until or unless there is no polarity, there is no interaction, right? So this is the different possibility of hydrogen bonding, and many factors will influence here, like what is the hybridization, and what is the orientation. So the strength of this hydrogen bond basically depends on the various factors, right? So see this strength of any hydrogen bond, if I am considering this is a general representation of this hydrogen bond, so strength can be determined by the enthalpy of this reaction, delta H dissociation. This will determine the strength of this bond, right? Strength of this hydrogen bond. This is called hydrogen bond. This is delta negative, this is delta positive. Oh, sorry, delta negative, this is delta positive. See, on the basis of this delta H, we can say that if delta H varies, this delta H dissociation varies from 10 to 50 kilojoule, then such type of hydrogen bonds are said to be weak hydrogen bonds. If it varies between 50 to 100 kilojoule, then this is called a strong hydrogen bond. A strong hydrogen bond. And if it is greater than 100 kilojoule, then it is called very strong hydrogen bond, right? So, you know, in first case, what I have taken here, ion dipole type interaction, generally they form very strong hydrogen bond, means the bond energy is more than 100 kilojoule. So, the hydrogen bonds belonging to type A, belonging to type A have bond energy greater than 100 kilojoule per mole, right? So basically the strongest hydrogen bond are the, I mean, belongs to the ion dipole interaction. Like one example I have shown here, other example you can see that and so if you see here, this is a negative ion, and this is this. So here also you are getting, this is ion, this is a neutral molecule. So ion dipole interaction, ion dipole. So this is the strongest, I mean, relatively this is stronger than dipole-dipole interactions, right? Okay, majority, but majority of example you have, they belongs to this category, dipole-dipole interaction, right? So you have various kind of hydrogen bonds like OH, NH, right? NH, NH, right? So there is some group is here attached, and some also here also attached. So I'm not bothered about all those groups. But in this situation, whenever exists, you will have this. Usually, see, we are considering that carbon hydrogen bond is what? Non-polar. Usually in chemistry, in organic chemistry, there is not much difference in the electronegativity, but sometimes this carbon hydrogen bond also may undergo the I mean hydrogen bonding, and this especially when this carbon is attached with some strong electron withdrawing groups. Like if you take this chloroform, strong 3 minus I affecting groups are there, so they are electron withdrawing groups, so accordingly the polarization will take place at here. So this also may enters in the hydrogen bonding with the compounds like this. So so sometime carbon hydrogen bond also may undergo what? Hydrogen bonding, but you should remember that it is possible only when there are strong electron withdrawing groups are present at the carbon. So this is what? Not frequently observed. This is not frequently observed. One more point I would like to discuss here, that what is the directional nature of this. So hydrogen bonds basically hydrogen bonds, they are directional. But this directional feature basically is more important when our this oxygen atom or any electronegative atom that is sp2 hybridized. In case of sp there is no problem. In case of sp3 also directional nature is not much important, right? So hydrogen bonds are directional. So what direction we are considering? Basically directional in the direction of directional in nature, in nature. And this directionality basically the directional nature of lone pair. I mean direction in which lone pairs are oriented. This the hydrogen bonds try to form in that direction, especially when the electronegative atom is sp2 hybridized, not for sp3 or not for sp. So this directional in nature and direction of lone pair, right? Directional in nature in the direction of lone pair, right? And this point is basically more important when this in organic chemistry for sp2 hybridized atom. So this point what I have written here, this is more important in organic chemistry when lone pair containing atom is sp2 hybridized, not sp3. When it is sp3 hybridized, then this has no much meaning. And one more point that this hydrogen bond try to be linear, linearity try to be maintained. So in most of the cases you will find the linear, but not in all cases, right? So some we can write here sometime not always, sometime linearity is favored in hydrogen bond, right? So let's see some example here. If we see this hf crystal, hf solid crystal. So see this hf, so this type of hydrogen bonding we are hydrogen bonds we are getting in case of hf, right? So this okay, well I have, F H, right? And then F H F H, right? This type. So this bond angle we found here 120 degree, right? This is 120 degree, and this from here to here, this length is 2.49 angstrom, right? So if you see here that this region, in this region from here to here, this will try to maintain the linearity. Bond angle around fluorine, this is different. But if we see the similar example of HCN polymer, if we see the HCN polymer, whole N polymer, then the hydrogen bond is linear. This type. So if you see here, so if you see here, so this lone pair of nitrogen is in the sp hybrid orbital. So in the sp hybrid orbital, this is linear. So basically here this is totally linear. So here we can say that this hydrogen bond forms in the linear fashion, and linearity here it is maintained, right? Here from here to here linearity is there, but not this in the crystal form. In the if you take 1 unit, 2 unit, then it will linear. But if you take a crystal giant structure, then this angle is reported experimentally, right? So this is the all about this directional and non-directional nature of hydrogen bond. So sometimes it is important and sometimes it is not important uh, for the formation of hydrogen bond, right? Now see uh, types of hydrogen bond. Types of hydrogen bond. Now see types of hydrogen bond. So we have mainly two types of hydrogen bonds. One is called intermolecular. First, intermolecular. Intermolecular hydrogen bonding. Hydrogen bonding. So intermolecular hydrogen bonding, or we can say association. Association. So in this case, two or more molecules. It is not, requirement that both the molecules are same or both the molecules are different. So when there is a hydrogen bond, or hydrogen bonding involves two or more molecules, then it is called hydrogen intermolecular hydrogen bonds. So this type of hydrogen bond involves two or more same or different molecules, right? Like HF and HF, water and water, right? Water and ammonia, right? And chloroform and you can take acetone, right? So all these are example of what intermolecular. One more, between two carboxylic acid molecules HCO, right? So here also two molecules are involved. So this is also called intermolecular hydrogen bonding. So this hydrogen bonding we are getting in vapor phase, or in non-polar solvent, non-polar solvent. So in this intermolecular hydrogen bonding, similarly, if we take some compound like this, para nitrophenol, right? So this is also intermolecular hydrogen bonding. So in all such cases, in case of intermolecular hydrogen bonding, intermolecular forces, molecular association takes place, molecular association takes place. Result of molecular association, intermolecular forces increased, that is intermolecular molecular forces increase. Result of which, if intermolecular forces are increased, so consequence of this, that volatility decreases, volatility what decreases. In this case, the volatility of molecule what will decrease. So if volatility will decrease, then boiling point increase. Volatility means tendency to convert into the vapor phase. If it is increased, boiling point obviously decreases. Solubility in water, increases. Sometimes density in case of water, in case of water, density of ice is less than density of H2O liquid. This is due to hydrogen bonding, intermolecular hydrogen bonding. See, one water molecule can form maximum 4 hydrogen bonds. One water molecule so see, so one water molecule can form maximum 4 hydrogen bonds, and due to this is 1, this is 2, this is 3, this is 4, and this is one water molecule. So one water molecule can form the maximum 4 hydrogen bonds. So in case of ice, there are maximum number of hydrogen bonds, and result of which what will happen, cage-like structure, cyclic structure will form. So although the structure of ice is very technical and very typical, but with this you can explain this anomaly, that the density of ice is less than density of water. This is the reason why the water is liquid at room temperature and H2S is gas also. See, H2O is liquid at room temperature, but H2S is gas at room temperature. This is also due to you can say hydrogen bonding, more strong hydrogen bonding compared to the H2S in case of water. We can assume that hydrogen bond may be present here in H2S also. And remember, hydrogen bonds can exist in all 3 phases, solid, liquid and gas. All 3 phases may have hydrogen bonds. Don't be stick only in liquid phase or only in solid phase. Gaseous phase also you have hydrogen bonds. See, one example I have shown you. Vapor phase or in non-polar solvent you will have hydrogen bond. So this also due to you can say here hydrogen bonds are stronger and more. Hydrogen bonds are stronger and have more number. Because I cannot say that H2S cannot form hydrogen bond, because this H2S sulfur has delta negative and hydrogen has delta positive. So they can form, but here hydrogen bonds are strong. So this is the reason. So this solubility, boiling point, and this volatility, you can explain on the basis of this intermolecular hydrogen bond. Similarly, second one is the intramolecular. Second one is intramolecular hydrogen bonding. So this is also called chelation, right? Chelation. What is the meaning of chelation? Formation of ring. Formation of ring. See here, this is also a ring formation is taking place here, but this is not called chelation because this ring is formed between 2 molecules. If ring is formed within molecule, so formation of ring within molecule, then it is called chelation. So it is clear that this intramolecular hydrogen bond is formed within molecule. So this type of hydrogen bond formed within molecule. Within molecule. For example, if you take orthonitrophenol, orthonitrophenol, so in case of orthonitrophenol, there is a hydrogen bond, and this hydrogen bond is called intramolecular hydrogen bond. Now tell me, intermolecular forces increases or decreases? In this case, intermolecular force decrease, because there is less interaction between molecule to molecule, right? Okay, intermolecular forces if decreases, then what? Volatility, because both were inversely. So volatility increases. Volatility increases, intermolecular forces decreases. So solubility in water decreases, and such type of compounds are practically insoluble in water, right? And boiling point decreases. Boiling point decreases, right? So these are the changes in the properties of molecules due to this uh, intramolecular hydrogen bonding. Now see some more example, like if you take salicylaldehyde. So this is salicylaldehyde. So this is intramolecular hydrogen bonding. Due to I mean, volatility increases, solubility in water decreases. So these are certain examples of intermolecular or intramolecular hydrogen bonding. And you know how the properties of changes with this. So this is I think it is sufficient for this your hydrogen bonding, right?